Great. Thank you everyone for coming. So I have to spoil this right away. There won't actually be 9001 ways covered in this talk. This was clickbait. But yeah, thank you all for coming. I'm Josie and I work as a consultant at Red Hat. And yeah, I'd like to take you on a little tour of some of the fun ways that we can exploit containers. So, because we'll be talking about like a lot of low-level Linux concepts, this talk will be also kind of dinosaur themed to keep your interest. And every now and then I'll do like a little recap of the things we covered in dinosaur terms. So yeah, hopefully you'll not fall asleep. Yeah, a little refresher on container basics. The way most developers will most likely interact with containers is just through a simple text file, so a Docker file, or in the more vendor-agnostic term for this, container file. And yeah, it's meant to package your code, any files you need for it to run, and its dependencies, libraries, in a way that you can run it anywhere. That is the idea behind it, really. So the real benefits it sort of promises over using VMs or something like that is that it's supposed to be portable, scalable, fast, and isolated. So there's a little bit of foreshadowing here. We'll see how isolated they really are. And in more low-level terms, just like there is no cloud, but just other people's computers, there is also no container, really. It's, if you run it on the system, it's just another process that's running on the system. So as far as host separation mechanisms go, you have these namespaces. Basically, all the yellow boxes on top is one container. And those are meant to isolate the various system resources, so like the process IDs, network interfaces, and mount points. And then that yellow box is capabilities. And those just assign specific privileges to processes without granting full root access. So an example for that would be maybe binding a privileged port for a server or something like that. And then you have the C groups. And those manage and limit resources, so like actual hardware type resources like CPU, memory, or I/O. And they limit how much of those the processes can actually use. In between, we have the container runtime. And the container runtime kind of manages the life cycle of these containers. So starting them, stopping them, removing them. And they do that by interfacing with the kernel. And they also sort of provision these namespaces and capabilities and C groups required to run them. Right, and then we also have the security modules that help in that regard. So security modules in the Linux kernel are like a framework to sort of provide a standardized way to plug in additional security policies and access control mechanisms. And yeah, they mostly focus on files and system resources. And then at the bottom, of course, you have the hardware that you're running on. There are some interesting topics there as well to be discussed, like around confidential compute and confidential containers as well, where you can run containers with encrypted memory and the likes, but we'll ignore that for now. All right, and in Jurassic Park terms, the hardware is the park that we're playing in. Then the kernel parts are like the guards or the control room. And then the individual containers are like the little dinosaur enclosures. All right, let's take a look at the attack vectors you have in those containers. So a lot of them can really be avoided by configuring things correctly, like many things. The container escape stuff we'll be looking at today happens in this purple box, really. So it's at the intersection of the host OS because what container escape really means is that we break out of the container and take over the host resources. And yeah, it kind of intersects with the container runtime, the host OS, and the container itself. So those are the major types of container escapes. So the file system ones are when processes gain access to the host's root file system, and that can, well, most of the time this happens through a misconfigured or overly permissive bind mount. I'm very comfortable in the Kubernetes world, so this is something you see quite commonly in the Kubernetes world, where people just use stars in their RBAC policies, and yeah, that's not good. And for memory, you can cause a buffer overflow in a containerized process and then manipulate shared memory regions. And the container runtime itself, if you misconfigure it, you can execute commands directly on the host system and bypass some of those boundaries we saw earlier. And the most interesting part, in my opinion, is the kernel type escapes. And it's mostly around gaining elevated privileges on the host and then bypassing isolation that way to gain direct access to the host system. And we'll take a look at one particular practical case of escaping the kernel now. eBPF was originally designed just for packet filtering. So the BPF is Berkeley Packet Filter, and it was later extended, that's what the E is for, to also allow running user space code directly in the kernel without loading LKM drivers. And the sort of marketing tagline they used to use is that it does to the Linux kernel what JS does to HTML. But they kind of cut that out, probably because JS is kind of a bad look to be associated with nowadays. And yeah, the major benefit of it is really that developers don't need to know how to write kernel code, and it sort of lowers the barrier of entry to running things directly in the kernel, which is also considered safe, and you get performance advantages, of course. And it's the most popular and well-known use case for eBPF right now is maybe Cilium. I don't know if you've heard of that. It's a CNI for Kubernetes, and they're also a Swiss company and recently acquired by Cisco. So the attack vectors you have in eBPF are, on one side, the eBPF verifier, which you can exploit by just tricking the kernel into loading unsafe bytecode, and you can use arithmetic and logic errors. There's the just-in-time compiler that you can also manipulate with errors, and then finally just memory corruption. So the particular case we'll be looking at uses the eBPF verifier. So it's meant to sort of ensure the safety and security of eBPF programs before they're executed in the kernel, and it operates in 2 steps. And you can kind of think of the verifier as the electric fences in Jurassic Park, and they're designed to keep the dinosaurs from running wild and causing chaos in the kernel. And before a new dinosaur is allowed into the park, the verifier makes sure that the enclosure is safe also. So it checks the basic layout in the first step to make sure there are no hidden tunnels or blind spots, so unreachable instructions or loops in the code. And then park security that goes and checks the cage and wiggles the lock and verifies and simulates all the possible behaviors of the dinosaur. You ensure that the dinosaur doesn't try and headbutt the fence or execute an instruction. Yeah. So yeah, the first part is like the electric fence, and the second part is like the rangers in Jurassic Park terms. So in the wild, there have been 3 sort of high-profile CVEs associated with using eBPF as a means of breaking out of containers. One of them was disclosed like quite recently by Google last month, and we'll be looking at an older one though. And they all have one thing in common though, which is the main thing that made them work was maths. So it works because of this arithmetic logic in the eBPF verifier. And it works because only the true conditional path is analyzed by the verifier, and we can put whatever instructions we want to in the false path, and the verifier will accept it. And the instructions in the dead path will then be patched. And you can manipulate the counter in there and cause an infinite loop. And we can just use denial of service in there by launching lots of instances of that exploit, and then locking up all available kernel threads. And yeah, that then in the end messes with the register, and we achieve arbitrary write. And from there, we can then just go look at the thread's task struct address and find the cred strut and set the ID to 0, and voila, we have root. So the analogy here is that there's a blind spot in the fence where the cameras can't see, and the raptors can escape if they hit the fence just right. All right, we'll have a little demo now. Let's see if this will work. Give me 1 second. Alright, I'll just reboot real quick. Alright, sorry about that. So I'll make it a little bit bigger. Can you see the... Oh, why is it black? Alright, there we go. Sorry, the demo gods were not with me. Alright, so we have a simple Docker file here. So this is a Ubuntu system, a Ubuntu VM, and also a Ubuntu container. We add just a regular demo user, and we switch to that user, and then we build the exploit after. And I'll add another tab to show you the running processes, and a tab to run I'm going to run BPF trace, which allows us to see the syscalls made by the eBPF program. And I'll run the Docker container. Okay, so if we check now, so we're the demo user. And by the end, we should be root. And just run the exploit here. And in the meantime, we can take a look at the processes. So right, that's not what I wanted to show. Sorry, messed up my screen. Well, in the background, it's messing around with the arithmetic stuff that I mentioned. It's making all those syscalls, and eventually it'll exhaust all the available kernel threads. And let's hit run here. And it takes a little moment. All right, so now if we run whoami, we're root, and we're in the root user group. And we can do now, for example, let's look at mounts, and we can actually mount the host file system. And yeah, we can use that to write files to the host and other fun things like that. Well, so yeah, that's we got root on the machine. So what now? So there are a bunch of fun things we can do with those permissions. So we can go explore the network. We can do data exfiltration to steal credentials and files. We can do lateral movement, so we can spawn additional privileged containers if we want to run more things and be undetected. And of course, establish persistence and install a backdoor. Can spread ransomwares in the systems. And if it's like a mail server, for example, we can use it to run a phishing campaign or things like that. So yeah, exploring the network is like a dinosaur looking for weak spots in the fences. And the data exfiltration, downloading sensitive info like the dino feeding schedules or the electric fence codes. And lateral movements is like the raptors. Once they're loose, they move from one enclosure to the next. And yeah. some establishing persistence or installing a backdoor is like the hidden nest in the visitor center in Jurassic Park. And then for ransomware and phishing, I don't have examples because they're kind of self-explanatory. So what can we do to prevent things like that? Maybe I have to say that I demoed it on Ubuntu because it never worked in RHEL. And that is because there are a lot of access control things baked into the system. So like SE Linux, the security enhanced Linux that has mandatory access control to prevent runC from being overwritten. So runC is a container runtime. And also, if you did get root on a system and you tried to disable SE Linux, you'd have to reboot the system in any case. So you'd definitely notice. It wouldn't be like a stealth attack. There's also AppArmor, which is similar to SE Linux in the sense that it has this mandatory access control model. But instead of being policy-based, where you write policies, it's path-based. And then there's also secure computing mode, which is a kernel feature that restricts the system calls a process can make. And yeah, it's meant to ensure that if a malicious program gets inside a container, it can't easily make a jailbreak by exploiting these system calls. So how does an exploit like that even end up in our containers? The most common way is like a supply chain attack, and there are a lot of different attack vectors in there. So you can tamper with the source code, you can tamper with the container file, you can attack the machine that actually runs the build for the container. Using vulnerable base images is a big thing. If you're using public registries, it's quite common that people sort of typo squat. So if you mistype Ubuntu or something, you might think you're downloading a Ubuntu image, but it's actually a vulnerable image that just looks like Ubuntu. And of course, dependencies, that everything you package into a container has the potential of having vulnerabilities or CVEs in it that people can exploit. And then finally, the registry, the stored images can be tampered with. And of course, then when it's deployed, you can also tamper with that. So the sort of proposed solution to that, which is like more or less the state of the art, I guess, is using trusted software supply chain solutions. So Red Hat has a lot of open source projects going on in this space at the moment. So some of them are meant to help at the code level, some at the build level. Most of them use cryptography in some way to sign the images, and then you can also verify at runtime that what you're running is actually a trusted image. And with regards to like vulnerabilities, there's maybe you've heard of SBOMs, the software bill of materials. So you can actually have a really detailed breakdown of the actual things you put into your container images and what is vulnerable, what needs to be patched. And it's a lot more actionable. And the whole approach is really based on shift left methodology, so catching vulnerabilities and issues as early as possible, so you don't have to go fix things further down the line when it's more expensive and takes more time to actually fix. All right. If you're interested in the topic, I have some suggested further reading. So these 3 books are really valuable, I think. And there are a lot of blog posts also around that space. And yeah, if you have questions for me, I'll be around at the conference. And you can also reach me at josie@redhat.com. And yeah, I think we can open it up to questions.
Nice one. Thanks very much. Have you got any questions, Josie? You good?
Thank you very much for the presentation. As eBPF now is starting to be touted in all sorts of products, by surveillance, politics, even one that I know of, and other companies. Do you think we're going to start to see more and more issues with code getting into the kernel and sort of like, will the verifier have to be really hardened or improved to stop some of these potential escapes going on?
Yeah, definitely. So yeah, adoption is definitely increasing in a lot of products. Personally, I'm kind of split on whether it makes sense in most of them to even use eBPF over like some other frameworks. But yeah, the verifier is kind of the biggest weak point, I think, at the moment. And the exploits are fairly complex, and they're also complex to fix in many cases.
Another question,
Yeah, thank you for the lecture. I just wanted to ask, that demo you showed us, it was on Linux. So would you be able to take kind of admin on a server else based on Windows or anything else? Would that still apply for other operating systems?
Not with this particular exploit, but it's a good question because eBPF is now also like semi-supported on Windows. But this exploit was particular for Linux.
and the others. Yeah, my sense today.
Hello. Do the exploit techniques significantly differ between different container engines such as Podman and Docker?
Yes, that is actually an excellent question because I tried to get my exploit working with Podman first and it didn't work. So yeah, the main difference probably is around how it handles permissions, and especially with Podman being more rootless by design.
Any more? Okay, well, as Adam said yesterday, I'm not going to stop everybody from getting to lunch as well. So should we give Josie another big round of applause?